Hi, everyone. I'm very happy to be here. This is a joint work with Ben Berger, Michal Feldman, and Amos Fiat, all from Tel Aviv University. And let's start. So, why is it not? Okay. So we're talking about discrete subdivision, and the setup is that we have m indivisible goods, n agents, and a valuation function for each of the agents. And the goal is to find the partition of the set of items, giving one bundle to each agent, such that it is fair. So we'll go into what fair means, but first, a few applications you can think of. There are numerous applications, so could be used for divorce settlements, inheritance, allocating course slots to students, or allocating labor or house chores to family members. There are many, many different areas you can think of, and the problem is natural and very suitable to many different directions. Okay, so let's go into what do we mean by fair. So one of the most well-known studies, most well-studied notions of fairness in fair division is Envy-Freeness. An allocation is envy-free if for any two agents I and j, agent I prefers the bundle of her own bundle xi to the bundle of agent j xj, or in other words, no agent envies another agent. And the problem is that we cannot guarantee existence of an EFX allocation, even for very simple instances. So think of, we have just one good and we want to allocate it to two different agents. One of the agents has to get the good and the other agent has to envy because he has an empty allocation. So we need some relaxation to be able to say anything meaningful. And arguably, the closest relaxation to actual Envy-Freeness is Envy-Freeness up to any good, EFX, which we study in this work. An allocation is envy-free up to any good, or EFX for short, if for any two agents, agent I prefers her own bundle xi to the bundle of agent j minus any item g from that bundle. So it's possible that I envies j, but if we remove one item from the bundle of j, regardless of what item it is, there will be no envy. To make this sink in a bit more, I'll show an example. First, we call this notion strong envy. So when we say that no agent envies up to one good, we mean that we say that no agent strongly envies another agent. So take a look at this profile. We have two agents, valuations are additive, and we have three items. A TV, a book, and the skateboard. Alice gets the TV and Bob gets the book and the skateboard. Now notice that Alice envies Bob, but moreover, Alice envies just the book that Bob has. She doesn't care about the skateboard, and even if we remove the skateboard from Bob's bundle, Alice will still envy Bob. So this allocation is not EFX. Alice strongly envies Bob. But now if we swap the two bundles, Alice gets the book and the skateboard and Bob gets the TV. Now Bob envies Alice, but Bob doesn't strongly envy Alice because if we remove the book from Alice's bundle, then she just has the skateboard, and Bob won't envy the skateboard, it's just 7 for him. And if we remove the skateboard, he just has the book, which he also doesn't envy. Okay. So having understood what EFX means, does anyone have a question about that? That's like the basic notion. Okay. Having understood what it means, now let's see if we can actually guarantee existence. So we don't really know yet if EFX always exists. We do know some specific cases when there are only two agents with distinct valuations, or any number of agents that have the identical valuations. Plaut and Roughgarden showed that there always exists an EFX. And when there are three additive agents, there's always an EFX, as shown in the EC best paper from 20 and by Chudori, Garg, and Melhorn. Someone, David, are you asking a question? No. Okay, and other cases remain open. Moreover, no one knows any negative example of an instance with any number of agents and any type of valuation where it doesn't admit an EFX. So this is how much we know about this problem. And as such, it was deemed fair division's biggest problem by Ariel Procaccia in an article in Communications of ACM.
Can you for a moment just say what you mean by additive? Like when is it not additive?
Additive means that each item has a value, and the value of a set of items is just the sum of the values of items. A more general valuation will be just each set has a value. Each set of items has a value, and it doesn't have to be dependent on the values of individual items.
Thank you.
Okay. Okay, so since the problem is so difficult to make some progress in it, we have a further relaxation, which is EFX with charity. So we ask, what if some of the goods are allowed to remain unallocated and we don't have to allocate all the goods? So if we just don't care how many goods we allocate, the problem becomes easy, we just allocate nothing. But we want some guarantee to be able to allocate a good number of the goods, to allocate as much as we can. And Chudori, Kavita, Melhorn, and Gurita show in Soda 20 that we can always have an allocation where the set U is unallocated goods, and it contains at most n-1 items. And the goods that are allocated induce an EFX allocation, and no agent envies the set of unallocated goods. So the value of each agent for her own bundle is larger than the value of the set of all the unallocated goods. Okay, so I just want to note that we compounded two relaxations, right? We relaxed EFX to relaxed Envy-Freeness to EFX, and we relaxed EFX to EFX with charity. We can't skip the first step. If we look at Envy-Freeness with charity, it doesn't give us much more than just Envy-Freeness, because we still, if agents have identical valuations and the items are valued at all powers of 2, distinct powers of 2, then any allocation that we'll have, some agent envies another, unless we don't allocate anything. If we allocate something, some agent will envy another, and we can't have Envy-Freeness even with charity in that instance. So that's why we have EFX with charity. Okay, now we're ready to talk about our contribution. So first, at a high level, our contribution is new proof techniques for finding EFX allocation. And like as a slogan, when we reallocate items, we also sometimes recycle. So it shouldn't be clear to you now what that means, but it will be clear during this talk. And using our techniques allows us to prove the existence of almost full EFX for 4 additive agents, meaning we leave at most one item unallocated. We show that less items need to go to charity when there are an arbitrary number of agents. And we simplify known proofs for EFX results and show that known results that are for additive agents hold in a more general setting where agents are beyond additive, a broader class of valuations that is beyond additive.
By less items, you mean less than n-1?
Yeah, yes, n-2. But I will show the theorems next slide. Okay, so the main results. Just a reminder, this like the state of the art. n-1 are allowed to go to charity. And the main theorem is that for 4 additive agents, there always exists an EFX allocation with at most one item remaining unallocated, and no one envies that unallocated item. Our second theorem is that for n additive agents, there always exists an EFX allocation with at most n-2 items remaining unallocated. So we have one item less, but now it's additive valuation, and so the result was general valuations. And our results extend beyond additive to a broader class of valuations that include unit demand, budget-additive, and multiplicative valuation, among others. And I want to bring a caveat here. Since we wrote that paper, there was an extension that showed that the same result holds for general valuation. This was by Mahara in ESA 21. So n-2 all holds for general valuation, but still in this talk we'll mostly focus on the proof of theorem 2 because it's simpler and it exemplifies our techniques better to have some sense of what we do in our main theorem. Okay, any questions? Okay. So at a high level, the proof of all our results has the same proof template that was used by previous papers on EFX, including the EC paper from 20 and the Solar paper from 20. So we start with a fixed EFX allocation X, and whenever we have at least k plus 1 unallocated items, we show that this allows us to reallocate items and find a partial EFX allocation Y, which dominates X according to some potential function phi. Now, since the number of allocations is bounded, these steps cannot go infinitely, so we must stop at some point, meaning that we must end up with a case where with an EFX allocation that has at most k unallocated items. So this k for the main result, this k will be 1. So we assume we have 2 unallocated goods and show that we can make progress, and this proves that we have there exists an EFX with at most 1 unallocated item, and for the second theorem, the k will be n-2. Okay, so for the rest of the talk, we just have some fixed x, and our goal is to always find a dominating EFX allocation y, assuming that we have k plus 1 unallocated items. So how can we find a dominating EFXY? So I haven't told you what the potential function is, and it's really not very important for this talk. All I'm going to say is that if we find the Pareto dominating allocation, then we have made progress in the potential function. So just a reminder of what Pareto domination means. If we have an allocation Y that Pareto dominates an allocation X, this means that no agent is worse off, and at least one agent is strictly better off in Y compared to X. Okay, Pareto domination is one way to advance our potential function. In this talk, whenever we want to make progress, we just show that there's a Pareto dominating EFX allocation. Okay, so how do we find the Pareto dominating EFX allocation? The most basic technique is using Envy cycles. So consider the graph that has agents at vertices and an edge from I to J if agent J envies agent I envies agent J. Now we can just reallocate the bundles along that cycle backwards. And so we get a new allocation. Each agent in that allocation is in that shift of the cycle is better off, and no agent became worse off. So Y Pareto dominates X, and EFX is preserved because the set of bundles that other agents have hasn't changed, and I am better off, and the set of bundles that other agents haven't changed. So since I haven't strongly envied anyone in X, in the new allocation where I'm better off, I'm still not going to strongly envy anyone. So it's still EFX. So now, having used this technique, we can assume that eventually we have no envy cycle. But can we do something if we almost have an envy cycle? So what if we just need some edge that comes into agent 2 from anyone, doesn't matter who. Now remember that we also have an unallocated good, because otherwise we are done. We already have a full allocation that is EFX. So what can we do with this unallocated good? We tentatively add it to the agent 2, which is the source. Now, if this new allocation is EFX, then we're done. We found an EFX allocation that dominates the previous one. So we assume it doesn't. This means that some agent strongly envies this set, X2 union G. And now we consider the set Z to be the minimum subset of X2 cup G that someone envies. Okay, so since someone envies X2 cup G, this means that you can take the smallest subset of each agent that they envy and look at the one that is minimal among all agents. So there has to be a set that someone envies and no one envies a subset of. Okay, so let's say that agent 5 is the one that envies that minimal subset, Z. So we can allocate Z to agent 5, and by the minimality of Z, no one will strongly envy 5 in that reallocation. And then the rest of the cycle will be along the path that goes from 2 to 5 that we know that we have by the definition of this instance. Okay, now this was a bit vague, so we'll make it more formal in definitions. What do we mean by the minimal subset? So we first define most envious agent. And agent J is most envious of a bundle T if there exists a subset Z of T such that agent J envies Z and no agent strongly envies Z, meaning no agent envies a proper subset of Z. And now the most basic observation is that giving Z to an agent J preserves the EFX as long as we haven't made any other agent worse off. Okay, then the set Z, we call it the minimally envied subset of T. Okay, was that clear? Does someone have a question? Because it's like a basic notion in the proof. Okay. So now the next thing, the championship. This was introduced in the CGM 20 paper, the 3-agent paper. Let G be an unallocated item, and agent I, G champions J, if I is the most envious agent of XJ union G. So similar to what we did in that almost cycle example. We consider the most envious agent of XJ cup G. And the notation is a labeled edge, an edge that is labeled G from I to J. A simple observation about champion edges is that if I is the champion of J and I does not envy J, then G is in the minimally envied subset of XJ cup G. Meaning that when we look at the minimal envy set that I envies, it cannot not include G. It has to include G because otherwise, agent I envies a subset of XJ, which is a contradiction of the fact that I does not envy agent J. Okay, so now that we have this observation, we can in every case where there's a champion edge and no envy edge from I to J, we induce a partition of the bundle XJ of agent J into top and bottom half bundles, TJ and BJ, where BJ is the set of items that I didn't want, the champion didn't want, and TJ cup G is the minimally envied subset of the set XJ cup G. That's the set, the exact set that agent I, the champion, wanted. Okay, so this can be a bit confusing. I'll try to make it clear with some visual aids. But anyone has a question? Okay. Okay, so similar scenario to what we had earlier. We have a path, an NV path from 2 to 1 and a champion edge from 1 to 2. And we have G as the unallocated good. Now, by the observation we've seen earlier, this G champion edge decomposes X2 into T2 and B2, where B2 is the set that agent 1 doesn't want. And now we tentatively give G to 2, and we can do a shift along the cycle where agent 1 gets exactly the set that he wanted, the minimal set that he wanted, and all other agents get the set that they wanted from their envy edge. And now we have B2 remaining unallocated, which will be important later. Okay, this can be done regardless of the number of unallocated goods that we have to use in the cycle. So if we have like a cycle with a G edge and then an H edge, and then the remaining cycle is envy edges, we can do a similar thing. Just allocate each unallocated good to a corresponding edge and shift along the cycle. But if we only have one unallocated good, like in this instance, and we have two edges labeled by the same unallocated good in the cycle, we can't do a similar thing because we give G to one of the agents and then we can't give it to the other one. So we can't do a shift similarly to before. But what we can do is consider the sets that should become unallocated, the B2 and B3, and maybe able to use it. This is where the recycling idea comes. So the intuition is that the edge from 1 to 2, the champion edge from 1 to 2 releases the set B2 because agent 1 doesn't want these items. And thus, if we use this edge, we can simultaneously use an edge that allocates B2 to someone. So if we had the fact that agent 2 is most envious of X4 cup B2, we have this sort of edge. Okay, then we can do something similar with the B2 set to what we did with unallocated items. We can tentatively attach B2 to X4 and attach G to T2, which is fine for us because 1 didn't want B2 by the definition of this set, and 2 does want it from when it's attached to X4, and then we can shift along the cycle, and we know that some of the goods from this set remain unallocated because 2 is most envious of this set, which means that he envies some subset. Okay, now that we have this basic concept of champion edges and the more general idea of champion edges with allocated sets, we can prove the second theorem, the N-2 theorem. So first, we can prove the Soda 20 theorem with the N-1 item. Just a reminder. So here's the proof. We'll do a couple of simplifying assumptions. They're not necessary, but they just make the explanation easier. So we assume that the allocation X is envy-free, so there are no envy edges. And we assume that valuations are additive and every item has positive value to every agent. Okay, no item is zero valued. So this can be generalized by simply perturbing the values of the items, adding some epsilon to zero valued items. Okay, so given that, we have this observation. Each agent I has a G champion for every unallocated item G. Okay, why is that? So since G is non-zero value, agent I prefers Xi cup G to Xi, and agent I envies this set. So since there is some agent that envies this set, there must be a most envious agent of this set. It could be I, wherein like I champions I, it's a self-champion, but there has to be some agent J that's most envious of this set. So we have for every unallocated good, we have an edge labeled by that good going into every agent in the graph. Okay, now using this observation, we can prove the theorem. So here, keep this observation in mind. We're proving the theorem from Soda 20 of the N-1 good. It suffices to show that we can Pareto advance whenever there are at least n unallocated goods by our general proof structure. So let G1 to Gn be a set of n unallocated goods. And by the observation, agent 1 has a G1 champion, call it agent 2. Agent 2 has a G2 champion, call it agent 3. Repeating this logic, we go back until we eventually have to go back to an agent that we've already seen. We have to close a cycle where the champion edges are labeled by different colors or different items, which we call a colorful cycle. So each edge is labeled by a different good, which means that we can attach a different good to each edge, which is consistent with the shift that we've seen in the example. So because there's a colorful cycle like that, we can find the Pareto dominating allocation, as we've shown in this example. Essentially, we have something like this, only more goods and no envy edges. And this proves that we can always advance when we have n unallocated goods. So there has to be an EFX allocation with only n-1 unallocated goods. This proves the Soda 20 theorem. Now we prove our theorem using the ideas from the previous proof. So just a reminder, we showed that the n-2, we can find an EFX allocation with at most n-2 items remaining unallocated. And it suffices to show, again, by our proof structure, it suffices to show that given an EFX allocation X, we can Pareto advance if there are at least n-1 items unallocated. By the previous slide, we showed that if there are at least n unallocated items, we can Pareto advance. So it remains to consider the case where there are exactly n-1 unallocated items. Now we have this lemma where if we have exactly n-1 unallocated items, then there exists a colorful cycle unless the graph consists of n-1 parallel Hamiltonian monochromatic cycles, one cycle for each unallocated good. So what do we mean? A colorful cycle, just to remind, is a cycle where we have edges of different labels of unallocated goods, and a monochromatic Hamiltonian cycle is a cycle of the same color, of the same label of good that goes through all of the agents once. So now proving this lemma, we'll consider the case where there are exactly n agents, and then we assume there are 3 colors or 3 unallocated goods, but the same proof extends to any number of agents. This is just for convenience. Okay, so the proof of the lemma, similar to the previous proof, we start with agent 1. We know that it has a G1 champion. So let's call it 2. 2 has a G2 champion, let's call it 3. 3 has a G3 champion, let's call it 4. But now we are out of distinct items. We've already used all the items. So what do we do now? We ask who is the G1 champion of agent 4. If it's 2 or 3 or 4, then we have a cycle with a colorful cycle. So it has to be 1. Now we ask who is the G2 champion of agent 1. Has to be 2. Otherwise, we get a cycle here if it's 4, if it's here if it's 3, here if it's 4. And finally, we ask who is the G3 champion of agent 2. And again, if it's not 3, then we get a green, blue, red cycle, or a green, red cycle, or just self-cycle, self-champion with 2. So it has to be 3. And using this, continuing the same logic, we can fill in all the blanks until we know who the champion of each color of all of the agents is. And now this is a case, this is a possible case where there are no more edges in the graph. And notice that if there's even one extra edge, it will always close the colorful cycle. So at this point, given the lemma, we now have a structure where there is no colorful cycle, but can we do something to add another edge add a color. So here, this is where the recycling idea comes in. So can we use a set of allocated goods to add another color to this structure? Okay, so first, so just to remind how it works, if we had this type of edge, as we've seen, we can do a shift using reallocating that set, and we advance. So so we want to have this this generalized champion edge. Any edge, almost any edge will let us advance, and we just need to find a way to reason about these edges and how do we find them. So let's focus. We focus on a single monochromatic Hamiltonian cycle. Let's say the good G or G1, just to avoid having the subscript 1 all the time. So we just call it G, the red good. And okay, consider just this cycle. The D champion edges, by the observation we had, decompose the bundle into top and bottom half, where the bottoms, the BIs, are unwanted sets, the sets that the items that champion doesn't want to get. So can we recycle these sets? Now we have a theorem that if X is envy-free in every Hamiltonian cycle of G champion edges, for any unallocated good G, there exists a good BI champion edge for every I. So what do we mean by good BI champion edge? A good edge would be an edge from agent A to agent B, labeled BI, such that the path from B to A contains I. So this means, for example, if we have an edge, a B1 edge from 4 to 2, this edge is good because 1 is on the path from 2 to 4 along the cycle. Intuitively, why this is good? Why is this good? Because when we use this edge, it's possible that we will be able to fit in the edge from 2 to 1 that releases this B1 set. So this would be good because it's potentially useful to us in the reallocation. Similarly, this is a good edge because the path from 3 to 4 also includes 1, but this is not a good edge. This is a bad edge because the path from 3 to 2 does not include 1. And if we want to use B1, we won't be able to fit in the edge that releases B1 here. Okay, and this is also a good edge. So now using the good edge theorem, and we have the structure from the lemma, we can find actually many good edges, many edges that will help us solve, find a way to advance, but we just need one. So by this good edge theorem, there must be a good B1 edge with respect to the good G1. Okay, so let's say this is the edge. And now, regardless of what good edge we find, there will be a good colorful cycle that uses recycling. Why is that? Because the edge is good, we can use the red edge here to release the items in the bottom of 1. And then we can, it's allowed to use this edge, and we have enough colors in the rest of the structure to complete this colorful cycle with recycling. Okay, so regardless of which good edge it is, we can do that. And again, this is just a reminder of what happens here. Since the edge is good, we can do this kind of shift. So now, is this theorem useful if the structure is not just like very, very nice to work with, like we had after this lemma. So it seems like the good edge theorem thing can only be used if this is the structure, and any good edge will help us. Can we do anything when the structure is more complex? So this brings us to the main theorem. Just a reminder, the main theorem is that for 4 additive agents, there always exists an EFX allocation with at most 1 item remaining unallocated. And this is like the general proof structure that we have in the sketch in the paper itself. Okay, so given we have 4 agents, and we assume we have 2 unallocated items, G and H, which we label red and blue. We have 2 main cases. When X is envy-free, we can always find the Pareto dominating allocation using these recycling techniques. When X has envy edges, is not envy-free, then we can find a dominating allocation using with respect to the potential function phi, but it's more complicated. It's more like we sometimes need to analyze more than one step of transitions, and we need to be more careful about the case analysis here. But we know that the only structure that is not like immediate in that case is this one. Well, there's one envy edge, and there's this path of parallel G and H champion edges. Now, in this case, where X is envy-free, we split into cases according to the length of the red cycles and the H and the blue cycle. This splits into, without loss of generality, we get these 6 cases. And in each of these cases, we are able to use our recycling techniques to find a colorful cycle with recycling, or what we call a Pareto improvable recycling, Pareto improvable cycle in the paper. And just to give some sense of the more advanced techniques that we have to solve these cases, I'll have two more complicated examples. So in this example, agent 2 is most envious of X1 cup B3, and agent 5 is most envious of T3 cup B2. So not X3, just the top, T3. So we write this, the fact that it's most envious of T3 cup B2, we write it as an edge labeled B2 mid B3, meaning he wants to add B2 and discard B3. So we have this kind of graph structure. And the fact that we have this mid notation helps us because we know that when we use this edge, we are guaranteed to release the set B3. So we can use it somewhere else. So that's why if we have this edge, we can also use this edge simultaneously. And the set B2 is released by this edge, by the champion edge from 1 to 2 by the definition of B2. B2 is just the set of items that agent 1 doesn't want. Now we can make a shift where we simultaneously shift two edges like so, 2 allocated items, allocated sets of items like so. Okay, and in this example, we have that this edge releases B2 and this edge uses B2 and releases B3, which this edge uses, which allows us to do a shift without even using the unallocated item G. We only use it for the partition into top and bottom half bundle. Okay, so this was just to get the flavor of the techniques. I didn't go into the exact definitions of these because it's a bit technical and it's more interesting to see it visually. And Yeah, so using these techniques, we were able to always advance in all these cases, and in this case, we need to do something a bit more complicated. Yeah, and these are some examples of the solutions we had for these cases, where we found a cycle and the highlighted edges of the cycle. Yeah, that's it. So to conclude, our paper introduces new technical tools for EFX proofs, including item recycling, the generalized champion edges, and the Pareto improvable cycle, the colorful cycle, and colorful cycle with recycling, which allows great flexibility in reasoning about possible deviations from current EFX allocation. And the main result was that for 4 agents, we can always find an EFX if we are allowed to not allocate at most one item. And for a general number of agents, we can always find an EFX we're allowed to not allocate n-2 items. And for further directions, so we cannot use the same approach of advancing the potential function x when we just have one unallocated good, because there's an example by Shudari, Gard, Melhorn, Mehta, and Misra from EC21 that showed that an allocation where there are 4 agents and 1 good is unallocated, and there's no way to advance that potential function phi. Any EFX that dominates the current allocation will have a lower potential. So one direction would be to consider a different potential function. And another direction that we haven't explored much is reasoning about the path between the allocations. What kind of allocations can we encounter in this process of improving an allocation? All we say is we only reason about one step. Maybe in the more complicated cases, we reason about 2 steps. But if we could say something about the path between allocations, showing that some allocations, some problematic allocations are impossible to reach, or maybe something else about that path, how this partial allocation evolves from step to step, maybe we could discover something about EFX existence. And possibly there's a counterexample that shows that it's impossible to always find an EFX. Yeah, and that's all I had to say.